Okay, let's continue concept of reacting enolate centers with electrophiles, and let's add a new carbon-carbon bond. So we're going to do some alpha alkylations. This will be an enolate plus some kind of carbon electrophile. We're going to get the enolate by taking a ketone or an aldehyde, putting it in base, and our carbon electrophile will just be on the losing end of a polar bond. So a haloalkane will do. And we know everything that we ever going to need to know about haloalkanes because we've studied them to death. Okay, so let's figure one. This, of course, needs to have alpha hydrogens. If you don't have alpha hydrogens, you cannot generate the enol or enolate by putting it in base. Therefore, you can't generate the nucleophile. So, back to the example that we just did on the quiz. Acetophenone is a good candidate for this type of reaction because it's lopsided, it's asymmetric, it's got alpha hydrogens, but only on one side. So this is where we're going to start. If the molecules have alpha hydrogens on both sides, then we're going to have to start making some decisions. And it's not going to be particularly difficult when you see what we're up against. Okay, so first thing is, let's put this in base. Base takes the acidic alpha hydrogen. There it is. Forms the enolate. So in the presence of strong base, you make the enolate. There you go. And you've made water. All right, when that carbon reforms, this area of high electron density, the pi bond is going to reach out and grab hold of something. Let's have it be something enticing. There you go, haloalkane. So this now gets to be step 2. Here's my haloalkane in step 2. That reforms. Is that an SN1 or an SN2? It's not a trick question today. Is that an SN1 or an SN2? It's an SN2. All the arrows go in one step. There's no carbocation. The leaving group leaves as the nucleophile attacks. And this looks like we saw the other day, like, oh, this is, I've seen this kind of thing before, it looks like an electrophilic addition. One of these carbons, the hand is tied because you're reforming the carbonyl here. So nothing is going to be attached to that carbon. This new carbon is going to attach here. And after we're done, I'm going to show you a shorthand trick that you can all use. It's not chemically correct, but it's shorthand. I just made the chain a little bit longer than it was before. Okay? So this is good because this is a very, very simple example. We can make it much, much more complicated than this. And this is a way that we can make our chain grow. And look, the functional group gets remade. So I can take a molecule that has a functional group in it, I can lengthen the chain of that molecule and still leave the functional group intact. That's a really good idea. Okay, here's the shorthand. Writing the enol or enolate is the correct way. But after a while, it gets a little bit tiresome. Here's what you can do instead. Take the base, just dump the electrons on the carbon. It's not as chemically correct as this one, but it does leave out any doubt about which of the carbons in my molecule is now the nucleophile. It's right there. And in our next couple of sets of reactions, we're going to take these little fragments and turn them into big, ugly, branched molecules. And at some point, doing it the shorthand way gives you less opportunity to screw up. So, yeah. This is acceptable because these two are resonance structures of one another. You can put that negative here. They are resonance structures of one another. So it's not like we're breaking a really big cardinal rule here or anything. It's shorthand. It's not as chemically correct. We know that these reactions do go through an enolate, but that's a resonance structure of it, and it ties my nucleophile down to a particular carbon, and I know that that is where my chain growth is going to occur. Okay. So we said these molecules, these types of reactions get complicated when you have to choose between a right-hand side and a left-hand side. We've been using acetophenone because this side is excluded from reaction because there's no alpha hydrogens here. What if there are alpha hydrogens on both sides? What if there are alpha hydrogens on both sides and the branching is uneven? Let's do that.
Is it okay, this is a simple, stupid question, but like when you have bromide on the third step, is it okay to just put a plus sign with that? Because for me that helps out instead of just having
Oh, yeah, instead of just having it flipped and bromide?
Right.
Yeah, absolutely, yeah. All right, let's look at some asymmetric alpha alkylations. Now, the base that I used in that previous example was hydroxide, and hydroxide's fine. There's nothing wrong with it. It will act like a base, and it will form the enolate, and the enolate will go on and react. But there is a carbonyl in there. And it is possible that hydroxide reacts at the carbonyl by nucleophilic addition, as well as doing these reactions that we want to. So we're going to come up with, once I'm showing you this, we're going to come up with a new base that is big, powerful, but so bulky that it won't be a nucleophile, that it will not attach to the carbonyl and it will only act as a base. So if I gave you, pen's going up. Here's acetone. It's a CH3 here and a CH3 there and a carbon in the middle. When you draw the stick figures, we omit the hydrogens. But that's how things are going to be presented to you. Okay? When you look in the book and you look on the web and you look at all the examples that are going to be presented to you, they're going to be in the zigzag or stick figure representation. They're not going to show the hydrogens. It's now your responsibility to figure out, yeah, there are 3 hydrogens here, and 3 hydrogens there. I have alpha hydrogens on both sides. Acetone is symmetrical. Butanone now has 3 hydrogens on the left-hand side and 2 hydrogens on the right. But the 3 on the left are not entirely equal to the 2 on the right, because that's a primary carbon and that's a secondary carbon. Okay? And if my reaction has anything to do at all with carbocations, my preferred place is going to be here. And if you've got anything at all to do with carbanions, it would be here. We saw that when we looked at epoxides, that there is a difference. So that's not particularly threatening, right? No one's threatened by 2-butanone. How about now? It looks a lot more threatening, but it doesn't need to be. You just put your hand over the part that is causing you distress, because none of this is going to participate in the reaction. Okay? Lots of chemicals have ring structures in them. Ring structures are incredibly important in biology. And when this comes across your desk on the test and you go, well, I only learned the straight chain stuff. I know how to do this reaction when it's a straight chain. Just stick your thumb over the part that's giving you grief. How many hydrogens are on that carbon right there?
3.
There's 1 remaining. There's a carbon. That carbon has to have 4 bonds. It's bonded to this carbon, that carbon, and this carbon, which leaves it 1 hydrogen. And 2 on that side. So this is different. I'm going to put this in base. And the base of choice is going to be called LDA, that is lithium diisopropylamide. Branching, 3 carbons bonded through the second carbon. So those are isopropyls. Nitrogen's in group 5, so it always makes 3 bonds. So this should, for the amine, diisopropylamine would have a hydrogen here. I'm taking that hydrogen away, replacing it with the lithium, and putting a negative charge on that nitrogen. Negative charge on a nitrogen, that's a powerful base. That's a really powerful base. But you see how big and bulky the rest of it is? It's not going to be a nucleophile. This is not going to attach to carbons, but it will strip hydrogens out of the molecule. So this is a good base and a poor nucleophile. And if you see LDA written anywhere in the book, online, on your test, on a quiz, we're making enols, we're making enolates. That's what it's used for. It's a big, powerful base that will not do nucleophilic additions or substitutions. Okay, so I have a choice of, does the LDA go to the left or go to the right? Let's try. Now, I just showed you, hey, here's a really handy dandy way of doing a shorthand shortcut. And what I would normally do is write it all out on the board, have you strain to figure out which one is better, the green or the red, and then tell you, no, 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 you've got it wrong because you wrote the carbanion in, right? So if I localize this as a carbanion, carbanions are the opposite of carbocations, right? So would a carbanion like to be on the least substituted or the most substituted side? Least substituted side, which would make you think, oh, let's take this one, which would be rational and wrong. And here's why. Because it's not really a carbanion. It's really an enolate. If we go by the red way, I get this. Let's add something very, very simple because we're really looking at the structure of this. Let's go ahead and just add, again, a bromomethane. The red way, frankly, looks the nicest. That looks like a happy molecule. Just hands up, having a good time. The green one looks, frankly, more difficult to do. Oh, it should have been in green. Okay. And you lose your bromide. Okay. Red and green, two different pathways. Which one happens? Depends. It depends. If you think about this as an anion, carbanion, and you localize it here, the left-hand side is better than the right-hand side. The red is better than the green. But it's not a simple carbanion. It's a carbanion that's in resonance with its enolate form. And so we're not going to look primarily to carbanion stability. We're going to look to alkene stability. And Zaitsev says, if you're gonna build an alkene, build the most substituted one. So this one, the red one, is not as good as the green one. This is the better intermediate. It is the better intermediate because Zaitsev says so, not because of carbanion stability. Okay, but there are two hydrogens here, and there's only one hydrogen there. There are two red hydrogens and only one green hydrogen, and these red ones are out in the open. And this green one is hiding behind this methyl, which we've conveniently not shown any of its bulk. And remember, our base is kind of big and ugly. So the chances of this getting to that hydrogen is small. But if it does, it makes the better product. The chances of taking either of these red ones is high, but it doesn't make as good a product. We've seen this kind of decision making before. What's it called? The green pathway to make the green product. It's the best product, but it's the hardest one to make. What product is that? Which makes the red one we did it in 1,2 versus 1,4 additions to dienes, where one pathway was easy to achieve but was not the best answer, and one answer was more difficult to achieve but was the best answer. The kinetic product, the top one, is the easy way out. There are more available hydrogens. They are easier to get to, but it doesn't make as good a product because it goes through an intermediate that is not as stable. The green one is harder to achieve, but ultimately you get rewarded by a lowering of energy for doing it. How can I control which one I achieve in my reaction flask?
It'll probably do the red one if you don't add anything to it. And then you probably have to add something to the green one. That'll make that more likely.
Okay, what do I add to the green one to make it happen? Heat. Okay. So this one happens hot, and that one happens cold. Doing the reaction cold, the reaction settles in on the easiest thing that it can get. Doing the reaction hot gives it time and opportunity to pick the best product. Okay? All right, let's look at some examples of alpha alkylations to the same molecule. So we're going to start with two aldehydes, and we're going to turn one of them into an enolate. And we're going to have that nucleophile now react with the other molecule of aldehyde or ketone as the electrophile. Got it? And we've seen it because we did it in lab. It's called the aldol. And the aldol comes in 2 steps and technically in 2 flavors, because you can do the aldol in acid or you can do it in base. I used to primarily teach it in acid because if you do it in acid, you stand a slightly larger chance of stopping the reaction halfway, because the aldol comes as an addition followed by a condensation. It goes in 2 steps. But it turns out that everybody really only does them in base, and they really only bother going all the way to the condensation. There's not really an awful lot that you can do to stop it going to the condensation. So let's look at those. So the aldol occurs in 2 steps. It is an addition and a condensation. And we are going to take 2. If we do it with aldehydes in the first example, then we really do make an aldol, because aldol means part aldehyde, part alcohol. But they could be ketones. And we're going to do this in base. I'm going to do it in dilute base. But the reaction will also work whether you do it in base or acid. If you do it in acid, it makes an enol instead of an enolate. And it doesn't quite go with the same power, but it still goes. And we're going to make what's called a beta hydroxy aldehyde or ketone. And then that molecule is going to lose a molecule of water. And it's going to make a molecule that's called an alpha beta unsaturated aldehyde. Again, or ketone. That's what you start with. And the first step here, that's the addition. And the second step, that's the condensation. Okay, let's look at the aldol addition. You need an aldehyde or ketone that has alpha hydrogens. Now, if we use an aldehyde, we can keep this really, really simple. I'll show you the simplest one we can possibly have. It does not get simpler than that. What's the name of this molecule? Two carbons. So it's an eth and al for the aldehyde. Okay, we're going to take two molecules of this aldehyde. One of them we're going to convert into a nucleophile, and the other one's going to act like the electrophile. The nucleophile generates the reaction, the arrow comes from it. The electrophile receives the reaction, the arrow goes to it. So in the first step, it's hydroxide. Do you want to localize the carbanion, or you want to do the enolate? Either way. I can put the negative charge here, which saves me bouncing it up and bouncing it down. It's less correct, but it's easier to follow. Sure. Let's do it. Let's see what it looks like. Okay. I think that's easier to see that that's a nucleophile than writing out an enolate. When you write out an enolate, there's a double bond and there's a negative charge on the oxygen, and it's not 100% clear that that carbon has come to react. That is a negative charge on a carbon. There is no doubt, or there should be no doubt in your mind that that is a nucleophile. Here is the second molecule of ethanol. This is my nucleophile. That's my electrophile. The carbonyl carbon is on the losing end of that polar bond. Nucleophile attacks the carbon. The pi bond in the carbonyl breaks. What type of reaction is that? hydrogens out because we are going to need them later. That's a nucleophilic addition. Aldehydes and ketones don't have a leaving group, so they don't react by substitution. However, they do have an electrophilic carbon, therefore they're susceptible to reaction with nucleophiles. That's a nucleophilic addition. I've got a negative charge on that oxygen. Now that oxygen has about with the negative charge, right, the alkoxide has about the same pKa as this hydroxide. And we know, because it was in the description, that this base is dilute, so it's absolutely swimming with water. Let's just go ahead and take it. All right. This is my aldol. It is part aldehyde, right there, and part alcohol, right there. The aldehyde is the most important functional group. This molecule has two functional groups. All of the molecules that you see in the remainder of the semester all have multiple functional groups in them. The aldehyde wins over the alcohol because it has two bonds to oxygen and alcohols only have one. So we're going to count positions away from the functional group. That makes that the alpha, that the beta, and this the gamma. And so this is a beta hydroxy aldehyde, which is what we said we were going to make. We've done it. That's the aldol addition. Now, the interesting thing, the product of the addition step still has alpha hydrogens right here, and you're still in base. So good luck trying to stop this reaction from snowballing, right? You've made something that you've taken something that had alpha hydrogens, which was good enough to react with base, and your product also has alpha hydrogens, so you cannot just pretend now that that is not going to react with the base. It will in the next step. Step 2 is the aldol condensation. I'm going to write it up a little bit. So you can just continue from where we are, or you can break this out into its own line. I'm going to break it out. Remember I said this reaction works if you did it in acid or in base. Doesn't matter. If I did it in acid, I would protonate this carbonyl, and I would form an enol, not an enolate. There'd be no negative charge. I'd make an enol. That enol would reach out, and my neutral product would be made fully formed. If I left it in acid, this alcohol would get protonated, turn into a leaving group, and leave. And that would leave a carbocation right here, and that's completely reasonable because that's a secondary carbon. And then I would do an E1 with a water molecule that's floating around, grabbing this hydrogen and building a double bond right here. So in acid, this would be an E1. I'm leaving it in base. You have hydroxide. There's the alpha hydrogen. It's acidic. It's going to be taken. So now I can take the electrons that are in that carbon-hydrogen bond and put them in one of two places. I could put them here. You're pushing more pi density towards something that already has it, okay. Or now hydroxide's not a good leaving group, but it's not stronger than the base that's causing the reaction to occur. That's an E2. In acid, this would be an E1. While you keep it in base, it stays as an E2. You just take that hydrogen, you're going to make a molecule of water here, and you're going to push off the hydroxide. So you're going to start with the hydroxide and end with the hydroxide. Nothing lost, nothing gained, until you look at the product and you realize something is gained. I'm missing a hydrogen right there. Okay. So that E2 is not the best E2 that the world has ever seen because my leaving group is terrible. Hydroxide, that's a strong enough base that makes that not be a good leaving group. But my base is not less powerful than my leaving group, so this reaction will plow forward. The reason that it really goes, though, is the product. What have I achieved in my product that I didn't have up to this point on the board? That's the alpha, and that's the beta. That's the gamma. So this is an alpha, beta, unsaturated aldehyde, which is what we were promised. What does the alpha beta unsaturated aldehyde have that none of the other molecules have? Two double bonds. Anything special about those two double bonds?
Pi bonds.
They're one single bond apart, which makes them my product has a conjugated pi system, so it wins. That's good enough. The E2 is not set up to succeed, but the molecule gets a conjugated pi system. That is a dramatic lowering in energy, because you can once you can conjugate and delocalize those electrons around, that's really stabilizing. So it wins. This is as simple as it gets. This can be absolutely anything, and it just carries through. It just carries through the whole way. Okay? Unless, of course, it's got alpha hydrogens on it. Then we have to make a choice. This also, right here, can be an R group, and it will carry through the whole way. Things get really, really interesting when both carbonyls are in the same molecule. We'll do those on Monday.